Good morning to everyone. Welcome to the DYNAmore Express webinar series. I'm Nikolai Lazarov and I will be the host of today's session. Today we'll talk about the new features in the official release of LSOpt, the version 7.0. And the overview will be given by the optimization expert in our house and also LSOpt developer Katharina. You can post your questions in the queue and we'll try to answer them after the session ends. Before we start, I would like to ask you to mute your microphones during the session and also to kindly appeal to fill in and send us the feedback sheet after the session ends. It would be very useful for us so that we can improve our service and I'll message the link in the chat after the end of the session. Thank you about that in advance and very appreciated. Okay, I would suggest to give it a go. Katharina, are you ready?
Yes.
Please take over.
Thank you, Nikolai, for the introduction. I'm going to present the new features in LSOpt version 7.0 today. I'm going to start with a general overview on the existing features available in LSOpt, and afterwards I'm going to present the new features that are available in the current version, which is LSOpt 7.0. LSOpt is a standalone optimization software, which means it can be linked to any simulation code or any type of program. Of course, we have some interfaces to LSDyna, but also to Excel, to MATLAB. And for process optimization, we also have interfaces to some preprocessors, LS Prepost, Primer, which is one of the new features, ANSA and Hypermorph. Those tools are very useful if you want to use LSOpt for shape optimization using morphing tools, for example, and also for result extraction. The interface is usually not needed if you run LSOpt with LSDyna, but for other types of programs it could be interesting. So we have an interface to MetaPost for result extraction. LSOpt can also be used for nested optimization. So we have an interface to LSOpt inside LSOpt and also LSTask. So it can be used for multi-level optimization. Of course, this is quite computationally expensive, but it is possible to do this in LSOpt. We also have a user-defined interface, so it's really possible to couple LSOpt to any type of program, which could be another finite element code or even self-written, let's say Python programs or whatever, can be coupled to LSOpt. While running an optimization, you usually do not just run a single or a few simulations. You usually run quite a lot of simulations. So it's quite common to run LSOpt on a local machine and only submit the LSDyna or solver jobs to queuing systems. That's why we also have interfaces to queuing systems like PBS and some others. Also here we have a user-defined option, and like this, LSOpt can also be used just as a process manager without running any optimization or robustness analysis or whatever. Of course, we have quite a few interfaces to LSDyna. For example, the star parameter keyword is supported by LSOpt, so it's quite easy to parameterize LSDyna models to be used with LSOpt for the optimization. LSOpt also supports the include structure of LSDyna, so it's possible to just use your standard models without doing any modifications. And actually the most important interface is the result extraction interface. So we have interfaces to the common LSDyna response types. That's what you see here on the right in the screenshot. We also have a checking of the LSDyna keyword files. Database files are checked to make sure that everything you need for the optimization is available and will be generated by LSDyna while running the optimization. And we also have a monitoring of the LSDyna progress. We also have a monitoring of the full optimization process, but also of the single LSDyna jobs that are running while you run the optimization. The methodologies that are implemented in LSOpt are the following. So in most cases, since we use highly nonlinear applications, usually if you run LSOpt with LSDyna or similar tools, a good methodology is to use response surface methods or the sequential response surface method, which is a very effective methodology, especially for optimization. So the idea is to approximate the real relation between the input parameters and the output values you need for your optimization, like the objective functions and constraints, by simple mathematical functions, which are called meta models. And we have several types of meta models available in LSOpt. Polynomials, in the simplest case, you could just use linear polynomials, for example. But we also have some nonlinear approaches like ready basis functions or feed-forward neural networks, which are useful for global approximations. As an alternative to the response surface methodology for optimization, a genetic algorithm is implemented in LSOpt, which is especially interesting for multi-objective optimization. So if the optimal solution is not unique anymore because of conflicting objectives, for example, then the genetic algorithm can be used to calculate Pareto optimal solutions. This is available direct, which means you only use simulation results to find the optimal values, and it can also be used meta model based, since the direct genetic algorithm requires many LSDyna simulations, so this is quite expensive, too expensive for most of the cases. That's why it can also be used meta model based. And as another type of application, not optimization, LSOpt can also be used for robustness analysis. So we have a Monte Carlo analysis approach implemented in LSOpt to consider uncertainties of parameters and evaluate the results, which is also available direct. So in this case, we only use simulation results to evaluate statistics, or again, if this is too expensive, the Monte Carlo analysis is also available meta model based. Apart from meta model approximations, there are also classifier approximations available in LSOpt. So we have support vector classification implemented. The difference between a meta model approximation and a classifier approximation is that the meta model approximation really approximates the value of the response, whereas a classifier approximates the constraint boundary. So just where in the design space is the design boundary between feasible designs, designs that satisfy all the constraints, and infeasible designs, designs that violate at least one of the constraints. This is especially useful for discontinuous responses, since meta models are always continuous functions, and also for binary responses, classifiers are very useful, and they can be used as constraints for the optimization or reliability analysis. Typical applications of LSOpt regarding optimization is, for example, size or shape optimization. Size optimization means that the optimization parameters are thicknesses of sheets, for example. Shape optimization can be done by incorporating also a preprocessor like ANSA or Primer, for example, or LS Prepost to do the shape modifications. Usually you use LSOpt with continuous parameters, but it's also possible to use discrete variables in LSOpt, and also mixed continuous and discrete optimization is available in LSOpt. So for discrete variables, we do not specify a certain range with a minimum and a maximum value, but we specify a set of discrete variables, for example, for sheet thicknesses. If we know that the sheet can only be manufactured with a certain set of thicknesses, so only, let's say, 2 millimeters, 2.5 and 3 millimeters, then it doesn't help if we do a continuous optimization and the optimal result is 2.7 millimeters, because we know this cannot be manufactured. And another application for discrete variables is if intermediate values even do not exist for the simulation. For example, if you have different materials you want to test and you want to find which one is the optimal value, then there is a material 1 and the material 2 and the material 3, but for example material 1.5 just does not exist. A very common typical application of LSOpt is parameter or system identification to calibrate material parameters, for example. I'm going to discuss this more detailed on the following slides. LSOpt has functionalities to optimize multiple load cases at the same time, which could be multiple similar load cases like a front impact and a side impact, for example, or for parameter identification, you could calibrate, let's say, a tensile test and a compression test and a shear test at the same time, but it could also be really multidisciplinary optimization, let's say optimization of a crash load case and an NVH load case at the same time. It's even possible to use different types of solvers for the distinct disciplines. Multi-objective optimization is available in LSOpt. So if the objective function is not unique anymore because of conflicting objectives, then LSOpt has functionalities to calculate Pareto optimal solutions. Multi-level optimization is available in LSOpt, so you could divide a huge optimization problem into smaller optimization problems and then use a multi-level optimization to optimize a few parameters in the inner level, use the result in the outer level to optimize some other parameters, go back to the inner level, and so on. And it's also possible to directly incorporate uncertainties of parameters in LSOpt. So it's like a combination of optimization and robustness analysis, which is reliability-based design optimization or robust parameter design. Since parameter identification or system identification is a very common application in LSOpt, we have some special features for comparison of test and simulation curves. So if you do a parameter identification manually, then you have your model, you have a few parameters, and it's possible to modify those parameters. Then you run your simulation, and then you just look at the plots and compare the test curve to the simulation curve. And if the fit is not good enough, then you modify your parameters and do the same thing again. Of course, for an optimization tool, it's not possible to look at a plot for comparison. So we need similarity measures for curves that can be used as objective functions in LSOpt. And this is what is available here. So we have the mean square error, for example. We have curve mapping, which calculates the areas between curves. And we also have dynamic time warping, for example, and some others for comparison of curves. It's not only possible to do parameter identification by matching global data like what you saw on the slide before. LSOpt also has functionalities for full field calibration. So the idea is to use DIC data, digital image correlation data obtained from optical measurement systems for parameter identification. So the idea is to use a deformation field, for example, or a strain field for comparison and match in time and space for the whole specimen, or at least a larger part of the specimen, like what you see here for the example of a tensile test. And the idea of comparison is the same than what we do for global data. The difference is that we do not just compare one curve, we have one curve per point in space and calculate the similarity measure for all those curves and optimize the sum of all those errors. LSOpt can not only be used for optimization, but also for sensitivity analysis. So LSOpt can be used for design exploration, for example, using the visualization features of the simulation points, the meta models, and so on in the post-processing tool of LSOpt. And also DOE studies for variable screening can be performed in LSOpt. We have two sensitivity measures implemented in LSOpt, which is ANOVA and SOBOL. So ANOVA is analysis of variance, which is a regression-based sensitivity measure, whereas SOBOL is a nonlinear variance-based sensitivity measures, and both can be used to get information on the contribution of variables to system performance and for the identification of significant and insignificant variables, and also a ranking of the importance of the parameters. So for large problems, large optimization problems with many possible parameters, it's quite common to first run a sensitivity analysis, for example, to find the most important parameters and then reduce the set of parameters for the optimization. But sensitivity analysis is also a useful tool to get just a better understanding of your model without running optimization afterwards. So this is also possible. A new feature in LSOpt of version 7.0, and I will go into detail later on, is principal component analysis as a new sensitivity measure. LSOpt can also be used for stochastic or probabilistic analysis. So the idea is to consider uncertainties of parameters, and like this, LSOpt can be used to test the robustness of a model by evaluating statistical values like mean values and standard deviations. So the idea is my input is a parameter or multiple parameters with underlying scatter. So I define a mean value and maybe standard deviation for my parameter, and the result I get is the scatter of the response caused by the scatter of my parameters. Also, correlation analysis is available in LSOpt. So in this case, I get information which parameter, for example, has more influence on the scatter of the response. Also, the reliability of a model can be tested, so the probability of failure can be evaluated caused by uncertainties of parameters, and LSOpt can be used to do outlier detection. And a very interesting feature, which is one of the few features that is restricted to be used with LSDyna in LSOpt, is the fringe of statistical results on the finite element model directly. This is what you see in the bottom left image here. So the idea is I do not just use a response, a global response evaluated at a certain time and judge on the robustness or on the scatter at that specific point, but on the whole model. And this is very useful to find, for example, different buckling modes, outliers, and also the critical areas, the critical region in my model. It is also possible to incorporate uncertainties into optimization. So we have robust parameter design. The idea of robust parameter design is to improve or maximize the robustness of the optimal value. So in this case, I do not minimize the value of the optimum itself, but the objective function is to minimize the standard deviation of a certain response or of certain responses. And there is reliability-based design optimization. So in this case, the idea is to improve the failure probability of the optimum. So of course, also those disciplines could be used in combination. If you need more general information on LSOpt and are interested in examples and maybe some applications, papers, and so on, then I'd like to refer you to the LSOpt support webpage, which is lsoptsupport.com. It actually also has information on LSTask if this is interesting for anybody. Now on the new features that are implemented in LSOpt 7.0. The first new feature is a principal component analysis I already mentioned before. So it's a new sensitivity measure that is available. And the idea of principal component analysis is to evaluate the influence of variables on histories or multi-point responses. A history is a value over time. So in this case, you, for example, do not just evaluate the sensitivity on, let's say, the maximal force or the displacement at the last time, but on the whole history over time. And you also consider that there is a correlation between values that are close in time. And multi-point response means that I do not evaluate a response, a scalar value, just at a certain specific point in my model, but for a whole part, for example, extracted from the D3plot files, or the whole model if necessary, if needed. And principal component analysis for the multi-point responses then also considers that points that are close in time are, sorry, not in time, but in space are correlated. So in general, the principal component analysis is a multivariate statistical technique. The idea is to reduce the correlated observations, so time values or special points, without losing information. So we do not consider all the values of a history or all the values of a multi-point response, but just the, we call it principal components, just a few components. To do this, we use a proper orthogonal decomposition of the correlation matrix of the data. And the sensitivities we get are the contributions of each principal component and also the cumulative history or multi-response sensitivity measures. And they can be visualized using bar charts like you see on the plot on the bottom right. And this can also be used for sensitivity analysis. We get a ranking of the parameters, and it can be used in the same way than the ANOVA or GSA results, but with the advantage that we use more data, the full history or all the multi-point responses. The next new feature that is available in version 7.0 is adaptive sampling, which uses classifiers. It's called explicit design space decomposition, or EDSD. Sampling constraints. So the sampling in this case is based on classifier predictions. How can this new feature be used? It can be used both in optimization or reliability analysis. So for optimization, it could be used to do the sampling only in feasible regions. Of course, since it's based on a classifier prediction, and this is just a prediction, we will always have some points outside the feasible region because the classifier boundary is adapted more and more over the iterations. And in the same way, it can be used for reliability analysis. In this case, we are not interested in sampling only in the feasible region, but we are interested in a better approximation of the constraint boundary, so the sampling is done near the boundary. This kind of adaptive sampling or sampling constraint works in iterative processes. So we start in the first iteration with a general sampling in the full design space. Then we get the first prediction of the classifier boundary. And from the second iteration, we can use those classifier predictions to do the adaptive sampling. It's also possible to only use a few points using the explicit design space decomposition. So you can decide, for example, to sample, let's say, every second point in the feasible region or near the boundary, and all the other points in the rest of the design space. The next new feature is that the Monte Carlo analysis, the meta model-based Monte Carlo analysis, is now available as a sequential strategy. So we iteratively add space filling, or in this case also the adaptive sampling I presented on a slide before can be used, new samples. And the convergence is we could stop depending on the meta model accuracy or on the probability of failure, depending on if we do a robustness analysis or a reliability analysis. In the images on the upper row, you see an example using space filling. So in this case, we do not use an adaptive sampling. We always sample in the full design space, but iteratively. So we improve the quality of the meta model in each of the iterations. And the meta model is used to evaluate the statistics for the robustness analysis or the probability of failure. So we can stop depending on the accuracy of the meta model, for example. And the row on the bottom shows an example using adaptive sampling. So the first iteration, of course, we do not have a classifier prediction yet. So in the first iteration, we sample in the full design space. And from the second iteration, we use adaptive sampling. So we sample more points closer to the boundary or in the area of the boundary of the constraint, and like this get a better prediction of the probability of failure, like you see in the optimization history in the image on the bottom left. So the probability of failure prediction is improved over the iterations here. The next new feature, this is more an IT feature, so probably not that interesting for most of the attendants of that webinar, but you could refer your IT to those new features. So there is a completely new job scheduler implemented in LSOpt. I won't go into detail here, but we have a support for SSH now, also support by the graphical user interfaces. So many settings regarding to SSH can be done directly in the graphical user interface of LSOpt now. If you use a user-defined interface to queuing systems, then there is a simplified version available. Before, it was necessary to provide a set of scripts that are used by the black box queuing system. So there is a simplified version now, which does not require any implementation of scripts anymore. And also the parallel limit is not valid anymore. So now you can run as many jobs as you want in parallel using LSOpt. Another new feature in version 7.0 is a feature regarding process management. So it's possible to deactivate and activate cases and stages. This is more like a debugging feature if you really have large process chains within your optimization, like you see in the example on the right. So you could set up your optimization, your full optimization from the beginning, and then maybe you realize that you don't have the scripts available yet you need for a certain stage, or session files are still missing, but it's already possible to run the finite element simulations. So you could deactivate the stages you do not already want to run and start running the others. And if you are ready with the next stages, then you can activate them and run the following stages and so on. Of course, there are dependencies between the stages, and also output from stages could be used as objective functions and constraints and so on. So everything that is related to a deactivated stage will be also deactivated automatically if you deactivate a stage or a sampling, and also the other way around. So if you activate it again, then also those entities will be activated again automatically. And the same for case deactivation, of course. Some minor new features. So LSOpt supports more command line options now. So if you want to run LSOpt in batch modes, there are quite a few command line options now available for archiving the LSOpt database. The repair operations are available now as command line options, the baseline run, and also clean functionalities. There is a list provided in the LSOpt manual, which explains all the command line options. And of course, there's also help command line options, which lists all the available command line options. And then we have a new interface to a preprocessor for shape optimization. We have an interface to Oasis Primer now. So you can specify everything you need for morphing and also the morphing parameters within Primer. There is a video available on YouTube in the Arab channel, which shows a nice example how to define everything regarding morphing and the parameters in Primer. Then Primer generates the design variables file. In this example, it's primer variable def.txt. And LSOpt has functionality to read all this information in LSOpt and replace the parameters, and then run Primer with the morphing tool to generate new geometries for shape optimization in LSOpt. And the last new feature LSOpt 7.0 has is regarding material calibration using partial curves. So we already talked about similarity measures in LSOpt before. We now have a modified version of the dynamic time warping. The standard dynamic time warping considers the full curve for both test and simulation curves, which has a problem that partial curves confound the error source. So we quite often have a shape with length mismatch, like what you see in the image on the bottom right. So trimming of the curves improves the curve compatibility and can reduce optimization complexity. So the idea is quite simple. The general idea of dynamic time warping is that we map each point on the test curve to a point on the simulation curve, or the other way around. So it might happen if we do not have the same number of points on target and simulation curves that we have a mapping of one point to multiple points or multiple points to one point. And the idea of the partial dynamic time warping is we look at the mapping, and if we realize that there are multiple points mapped to the first or the last point, then we just omit those points and get a shorter curve. And this is done iteratively until we have the same number of points for both the computed and the target curve. So this sensitivity measures is suitable for noisy curves. Already the standard dynamic time warping is of course suitable for noisy curves, but it's also now suitable for partial mapping of curves. So the curve distance measures or similarity measures that are available now in LSOPT are the ones you see here. We of course still have the mean squared error, which is suitable for noise and also partial curves, but the disadvantage is that it's not suitable for hysteretic curves. Then we have the partial curve mapping, which calculates the area between the curves. This is also suitable for partial curves, but the disadvantage, it uses the length of the curve, so it's not suitable for noisy curves, or it requires filtering if you have noisy curves. Then we have discrete Frege and dynamic time warping. Both are suitable for noisy and hysteretic curves, but they always compare the full curves, so they are not suitable for curves of unequal geometric length. And now the new feature, the modified dynamic time warping, which I explained on a slide before. This is suitable for noisy curves, for hysteretic curves, and also for curves of unequal geometric length. Of course, it's a little bit more computationally expensive than the other approaches. That's it on the new features of LSOPT. For more information, I'll refer you to lsoptsupport.com again, and I thank you for your attention. Are there any questions?
Okay, Katharina, thank you for the overview. Are there any questions from the participants? If you have any questions, please type them in the chat box. We'll try to answer them. Okay, perhaps I would like to ask you a question, Katharina, that perhaps may concern a lot of our customers. In which manner will LSOPT be used in the ANSYS environment after the acquisition of LST? I mean, will it be a separate package, or will it be purchased along LSDyna as a companion, or is it already clear at all?
I don't think that it's clear for the future in general. For now, it's still part of LSDyna, so it still does not require any additional license. So it's still the same. If you have at least one LSDyna license, you're also free to use LSOPT and LSTask. So it's the same than before, for now, at least. But I cannot promise anything for the future, of course.
Yeah, of course. Thank you very much. Okay, I can't see any question from the participants. Well, okay, so as you've already may seen, I posted the evaluation link in the chat with a kind request to fill it and send it to us. The presentation will be uploaded in the next days and will be available for you on the shown link. And of course, you will find a record of today's session on our YouTube channel. Of course, you can also feel free to contact us on support@dynamore.de directly if any questions should occur afterwards. A lot of useful information about LSDyna can be found in the listed links below as well. So, okay, hence there are no questions. I'll close the session. Thank you for attending. Stay healthy and see you on the next webinar. Bye from our side and have a nice day and have a nice weekend as well.